So now we've seen what PA equals LU actually is. It's an equation relating a permutation matrix times the matrix you care about, A, to a lower triangular matrix L multiplied by a matrix in row echelon form U. This equation is useful for all sorts of reasons. For one, you can use properties of U to define properties of A. So the rank and nullity of U is the same as the rank and the nullity of A. And then in the previous video, the one right before this, we saw how to use PA equals LU to drastically simplify the system AX equals B. AX equals B separates into two easier systems. LY equals PB, which is lower triangular, and UX equals Y, which is upper triangular. So the last thing to address here is, well, where do we get PA equals LU in the first place? And it should come as no surprise that this is going to involve row reductions. But the cool thing about this new algorithm, which looks a lot like Gauss-Jordan but has some key differences, is that here we can build all of the matrices concurrently. So I'm going to read the steps here and then we'll do an example. So we start with an m by n matrix called A. We're going to row reduce A, so we start in the upper left-hand corner where I and j both equal 1. We start with L equaling the m by m 0 matrix, and we start with P equaling the m by m identity matrix. So this is how we start, and at every stage we potentially make changes to L and P. So in step 1, what we do is we look at the position we're interested in. So when we start, we'll look at the upper left-hand corner, and then we're going to work our way to the right and down throughout the matrix. And if we're currently focused on a position that's equal to 0, we do the same thing we do in Gauss-Jordan. We switch with the closest row below that has a non-zero number so that we can use that row for a pivot. So the first step is a row switch if we are looking at a 0 position. And if there's nothing to switch with, we move right and down 1, and then we start again. So if we need to switch to get a pivot, we do so. If not, we move to step 2. Now, every time we do a row switch, we do the same row switch in L, and we do the same row switch in P. So again, we're building U, L, and P concurrently. Great. The next step is the elimination step. Once we have our pivot position, we are not going to scale it like we do in Gauss-Jordan because we only want to get to non-reduced row echelon form, not reduced row echelon form. We do, however, need to eliminate all positions below a pivot. So the way to say that rigorously is we subtract suitable multiples, m sub kj, of the ith row from the row we care about. So if we want to eliminate a position, we subtract the suitable multiple of the pivot row from the row we're trying to eliminate from. And what we do is we take that multiplier and we save it in the matrix L, but we don't save the multiplier, we save its negative. Finally, once we've cleared out all entries below a pivot, we move right 1 and down 1, and then we go back to step 1. So this is almost identical to Gauss-Jordan, except we are satisfied with pivot positions that are not equal to 1, as long as they're just not 0, and we only eliminate entries below pivots, not above pivots. The final step is once we're done, so once we get from A to U, which is in row echelon form, the last step is to insert 1s on the diagonal of L, and that completes the algorithm. So at the end of the algorithm, we will have reduced A to row echelon form U, and we have the equation PA equals LU. So the algorithm might sound like a bit of word soup, but I think that the examples really make this a little bit easier to digest. So let's go to widescreen and do an example. So I'm going widescreen here because I'm building multiple matrices at the same time. Keep in mind that because we are building multiple matrices at the same time, this is the kind of thing that computer scientists love because this introduces efficiency into the algorithm if we were to hard code it into a system. Okay, so remember how we start. We start with our m by n matrix A. In this case, it looks like A is 4 by 5. We start with L, which is an empty matrix, or another way to think of it is L is all zeros, and the size is number of rows of A by number of rows. So M here equals 4. So L starts off as the 4 by 4 zero matrix. And P starts off as the 4 by 4 identity matrix. So let's walk through this algorithm step by step. The key thing to remember is we change L every single step, where we either insert the negative of a multiplier n if it's an elimination step, or we do a row swap in L if it's a swapping step. P only gets changed if we're doing a swapping step. So what's the first step going to be in this algorithm? Well, I'm starting in the upper left-hand corner, and it looks like I'm actually happy with that position. I have a non-zero position in the upper left-hand corner, so I'm going to use that as my pivot. The problem is that all of the entries below my pivot are not zero, so I need to eliminate those entries using row addition. That requires 3 row additions here. We're going to take row 2 and add 3 times row 1 to get rid of the 6. Then we'll take row 3 and subtract 5 times row 1 to get rid of this 10. And then we'll take row 4 and subtract 6 times row 1 to eliminate the 12. So let's see that in action here. So I'm building U every time I do a row operation. So I'm taking row 2, I'm taking row 2 and adding 3 times row 1. So that zeroes out the 2, 1 position. And in this step, the multiplier I'm using to manipulate row 2 using row 1 is equal to 3. So what I do is I go over to L and I look at the 2, 1 position and I insert the negative of this multiplier, which is negative 3. Let's look at the second operation. The second operation here requires that I take row 3 and subtract 5 times row 1. So that's going to zero out the 3, 1 position. And the multiplier I'm using in this step is negative 5. So I'm using negative 5 times row 1 to manipulate row 3. So I go over to L and I look at the 3, 1 position and I insert the negation of the multiplier, which is equal to 5. Then I go to my last step or the last row reduction here. For this last row reduction, I'm manipulating row 4 using row 1, and the multiplier here is negative 6. That eliminates the 4, 1 position, and the multiplier in L will go in the 4, 1 position, and the multiplier was negative 6, so I need to insert 6 into the 4, 1 position. So that concludes the first step here, the first elimination step of this whole row reduction. Great. So now I've eliminated everything below my first pivot. So now I need to go right 1 and down 1 and look for my next pivot. Well, I have a 0 here, so I need to switch with the first available row that gets me a pivot, and that will be switching row 2 with row 3 to get an 11 as my new pivot. So the next step is to switch row 2 with row 3. And remember, whenever we do a row swap, we do it on U, L, and P. So I'm doing row 2 with row 3 on all 3 of these matrices. 1, 2, 3, go. So now I've switched row 2 with row 3 of U. I'm switching row 2 with row 3 of L. And I'm switching row 2 with row 3 of P. Great. So now I have a pivot position in the 2, 2 location of my U, but I need to eliminate all of the entries below this pivot, so I need to change row 4 here. The right way to do this is to take row 4 and subtract 4 times row 2. So now I have row 4 minus 4 row 2, and that will get rid of the 44 in the 4, 2 position. I've used an elimination step, so that means I'm going to insert the negation of my multiplier in the appropriate position of L. Remember, I'm manipulating row 4 using row 2, so this means I go to the 4, 2 location of L, and I insert negative, negative 4, which is just equal to 4. This was an elimination step, so I don't change P in this step. Now my second pivot is totally legit. Everything below it is equal to 0. So now I move right 1, down 1, and look for my next pivot. I won't get one in the 3, 3 position because I have a 0, and there's only a 0 below. So then I move right 1 and ask, can I get a pivot in the 3, 4 position? And the answer is yes, except I need to do a row swap to do it. So I have a 0 in this 3, 4 position. To get, I can switch that 0 with this 5 by switching row 3 with row 4. So now the next step is to switch row 3 with row 4. And remember, whenever we do a row swap, we change all 3 of U, L, and P. So let's do that. 1, 2, 3, go. So now we've switched row 3 with row 4 in U, and then we've done the same in L and P. And now if we look at U, we find that U is in row echelon form, but not reduced row echelon form. That's what we were looking for. So U now is in row echelon form. In particular, we can see that the rank here is 1, 2, 3, 4. So evidently A had rank 4. The algorithm now terminates, except the last thing to do is add 1s to the diagonal of L. So we need 1s on the diagonal of L. So we put them there. And now the algorithm terminates. PA now equals LU. So the final state of P is this matrix. The final state of L is, or I guess A was the original matrix here. The final state of L is right here. And then the final state of U is here. So you can verify yourself that this actually worked. Multiply P times A and check that is the same thing as L times U. So now that we have our factorization, we can use this factorization to solve all sorts of problems. You can determine the rank of A, like we just said, by figuring out the rank of U, which is much easier than figuring out the rank of A. You can also take any system of equations, AX equals B, and chunk it into 2 easier equations. Ly equals PB, and then UX equals Y.